Hello, this video is about moment generating functions, and I will also proceed to Kolmogov's theorem, probability generating function, Chern-Zwick law and strong law of large numbers as well. Let me start with the MGF one. So in the MGF, what is the basic pattern we are seeing over here? The moment generating is a function which creates the momentum of any statistically independent values. And there are obviously two types, like all time, which first one is a continuous one and the second type is a discrete one. You know that in continuous we integrate and in discrete we take the summation. Let me proceed with this. So mx of t equal to e to the power tx. Remember that this e is for expectation and this is the exponential t. And this is equal to e to the power tx into f of x into dx, obviously for a continuous function. And for discrete function, the formation will be e to the power tx into f of x. That's it. So this is the first two part. Remember that the mx also has a functional format, and that is e to the power tx can be explained in this way. That is e to the power 1 plus tx, you know the expression, tx squared by factorial 2 tqx cubed by factorial 3 t to the power r x to the power r by factorial r, and it proceeds like this. So finally you can represent how to incorporate the mu over here, which is the functional format. So here 1 plus t, this is nothing but e to the power x. So I'm taking the expectation of 1 is 1, expectation of tx is t of e to the power x, then t square by 2 factorial will be outside and it is simply e of x square. In this way we will be proceeding. I'm not writing all the terms. So t to the power r x factorial and exponential of, let me put it this side, x to the power r. That's it. And it keeps on proceeding. Now your job is to represent, we know that the very first one is mu1 dash, the first order raw central node. There's a t square by factorial 2, that is mu2 dash. In that way we proceed. So tr by r factorial mu r dash. That's it. So here you are going to use the summation, and as we are starting with 1, so the first value is 0 and it goes till infinity. T to the power r factorial mu r dash. That's it. So this is the normal process of doing it, where mu r is nothing but this mu r portion, mu r dash is nothing but expectation of x to the power r, which is nothing but infinity to minus infinity to plus infinity fx. Or there is another format, we keep on forgetting that, is this is x to the power r and fx. Remember that our main target is to just find the multiplied format. Just find the multiplied format x to the power r into fx and you're done with it. Now if we are about to find it, what we need to do is to differentiate the given function, that is this one. Okay, let me use a different color. Okay, let me use the good old white. So here if we differentiate the function with respect to obviously t, so d dt, and rth time if we differentiate it, then it will be mu r dash by r factorial. As first time is 1, so it's gone. Second is obviously with that our r factorial is also multiplied, mu r plus 1 dash mu dash r plus 2, and in this way next term will be t square by factorial 2 dot 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 at t equal to 0. If we proceed in this way and t equal to 0, so mu r dash value will finally be d dt, both are its order derivative, m of x t equal to 0. That's it. So this is the moment generating function x about the point x equal to a. So if we just put x equal to a structure, you can get your functional format. In general, we write it as the moment generating, that is mu r dash equal to e expectation of x minus a whole to the power r, where this is the rth order moment about the point x equal to a, rth order raw moment. Next, but there are some limitations of the moment generating functions as well. For example, a random variable x may have no moments although its MGF exists. Although MGF exists. And on the contrary, a random variable x can have MGF, yet the MGF does not generate moments. So these are the two very special cases where the entire law fails.